Okay, I welcome you all for today classes. In this today classes, we are going to start the new topic, that is the effect of a preheat in a multi-stage compression, or prove that preheat factor is always less than 1. Okay, so first we have to consider this temperature versus entropy. So this is a temperature versus entropy diagram. Okay, so here the overall isentropic efficiency is useful as it indicates the overall performance of the turbo machines. Okay, so what is the overall isentropic efficiency? So it will indicate that what is the overall performance of a turbo machine. So by getting the overall isentropic efficiency, we are going to know that the performance of a turbo machine, that overall performance of a turbo machine. Okay, but it is not always indicate the true efficiency from the hydrodynamic point of view. Okay, so which is measure of fluid losses within the machine. Okay, yes, this overall isentropic efficiency is useful as it indicates the overall performance of the turbo machines, but it is not to indicate the true efficiency from the hydrodynamic point of view. So what is this hydrodynamic point of view? So in the turbo machines we are using the fluid. Okay, it may be a water, or it may be a steam, or it may be a gas, whatever this. Okay, so from that hydrodynamic point of view, which is measure of a fluid losses, there is a losses in the turbo machines. Okay, there is a losses in the turbo machines. So if you have any losses in the fluid, so we are not getting the accurate efficiency or accurate performance of the turbo machines. Okay, so for that, this overall isentropic efficiency is useful for indicating the overall performance of the turbo machines, but it is not always indicate the true efficiency. See this word, true efficiency. Why it is not indicating the true efficiency? So from the hydrodynamic point of view, this is a measure of fluid losses within the machines. Okay, a compressor stage with a finite pressure stage is called as a finite stage. A compressor stage with a finite pressure stage is called as a finite stage. What is a finite stage here? A compressor stage with a finite pressure. The compressor. So in the multi-stage compressor, as you see here, multi-stage compressor, we are having number of stages. Okay, so in that stages with the finite pressure stage, if the stage is having the finite pressure stage, then it is called the finite stage. Finite stage. Okay, in a multi-stage compressor, in each stage efficiency depends on the inlet temperature of the fluid to the stage and pressure ratio in each stage. Okay, so in multi-stage compressors multi-stage compressor for the same efficiency, uh, in each stage efficiency, it depends on the inlet temperature of the fluid to the stage and pressure ratio in each stage. So it depends upon what? Inlet temperature. So for example, if I have taken here temperature versus entropy, or TS diagram, so you can indicate the different pressures here, the P1, P2, P3 and P4 pressure. So these are the pressure lines. Okay, pressure lines, and we are having the initial pressure of the turbine is P1 and the final pressure of the turbine is P4. Intermediate, in between these two we are having the two stages, stage 1, stage 2. It's 1 to 2 is the stage 1, 2 to 3 is the stage 2, and 3 to 4 is the stage 3. Stage 3. Okay, so each stage efficiency is depends upon the inlet temperature of the fluid to that stage. For example, if the fluid is flowing in this first stage with certain temperature, okay, its efficiency will gives us, it depends upon the inlet temperature of that fluid. Suppose that same fluid is entered to the next stage, that is stage number 2. So this efficiency of this stage, the efficiency of this stage is depends upon the inlet temperature of the fluid, whatever here it enters to the second stage. So that temperature, that fluid temperature is reason for the stage temperature, stage efficiency. Similarly, if the fluid is getting out from this stage and enter into the third stage, so similarly this third stage efficiency is again it depends upon the inlet temperature of that fluid. So whatever he has given here, see here in a multi-stage compressor, this is a multi-stage compressor. So here we are having stage 1, stage 2 and stage 3. Okay, so multi-stage sample in each stage efficiency depends on inlet temperature of the fluid to the stages and pressure ratio in each stage. So it is also depends on the pressure ratio in each stage. So here this each stage efficiency is depends upon what inlet temperature of the fluid and the pressure ratio of that stage. For example, if you get the stage efficiency here, it depends upon the inlet temperature of the fluid and the pressure ratio of this stage. Similarly, second stage. Similarly, for third stage. Okay. So next, thus in multi-stage compressor, for the same efficiency, each succeeding stage is suffered by the inefficiency of the preceding stage, which is handling the fluid at higher temperatures. Okay. So in the multi-stage compressor, for the same efficiency, the each stage is having the same efficiency. So even though in that cases, so each stage is suffered by the inefficiency of the preceding stage. Suppose here the stage 2 and stage 1 and stage 3 are having the same efficiency. Even though it having the same efficiency, it sometimes it suffered from the inefficiency due to the preceding stages and stages which is handling the fluid at higher temperature, which is handling the fluid at higher temperature. Okay, so this is a temperature versus entropy diagram. So here we are having three stages, 1, 2 and 3 stages. Okay, so this 1 to 1 4 double dot 4 double dash is indicating the overall isentropic work done. So see here 1 to 4 double dot is indicating the overall isentropic work done. Similarly, from 1 to 4, this will shows the actual work done, overall actual work done of that compressor. So this is indicated by a WA. This is the overall work done, actual work done of the compressor. And here this 1 to 4 double dot, 1 to 4 double dot is indicating the isentropic, overall isentropic work done, and this 1 to 4, this 1 to 4 is indicating the overall actual work done of the compressors. Okay, here this will indicates the pressure on P1, P2, P3 and this one is a P4. Okay, so this 1 to 2 is again it is a indicating the first stage actual work done, first stage actual work done, and this here this part is indicating the first stage isentropic work done. This is delta ws2 is indicating the second stage isentropic work done, and delta ws3 is indicating the third stage isentropic work done. Okay, so we are having three stages here. So this ws1 is the first stage isentropic work done, ws2 is the second stage isentropic work done, and ws3 is the third stage isentropic work done. Okay, so this will shows the temperature versus entropy diagram. Okay, so here next, So here again a three-stage compressor is considered between the inlet pressure P1 and delivery pressure P4. So already we discussed it. A three-stage compressor. So we are taking the three-stage compressor. Okay. So that inlet pressure is P1 and delivery pressure is of P4. In between these two pressures we are having P2 and P3 pressure. P2 and P3 pressures. Okay. Assume that a stage pressure ratio for all the stage is same. So already we have taken the pressure ratio of all three stages are same, that is P2 by P1 is equal to P3 by P4, P2 is equal to P4 by P3. The pressure ratio of each stage is considered as a same. Okay. Next, stage efficiency for all the stages are same. So even the pressure ratio in all the stages are same. Then the stage efficiency for all the stages are same. That is efficiency of stage 1, efficiency of stage 2, efficiency of stage 3 is equal to overall efficiency of the compressor. Overall efficiency of the compressor. These are all the same. Okay, let 1 4 double dot and 1 4 are the total isentropic and actual compression process respectively, or total isentropic work done and actual actual compression work done respectively. So it is shown here in this 144 here 144 and 14. These 144 is the isentropic work done, okay, or actual isentropic compression process, and this 1 to 4 is the actual work done, actual work done. Okay. So here we are having this. No, neta naught is the overall efficiency. Neta naught is the overall efficiency. WA and WS are the total actual and total isentropic work absorbed. So this WA is the total actual work absorbed, and this WS is the total isentropic work absorbed. Now we know that the we know that the efficiency, overall efficiency is WS by WA. WS is the isentropic work done. W is the actual work done. So this from this we can write that WA is equal to what? WS by meter. WS by meter. That we have to consider equation number 1. We have to consider equation number 1. Okay. For stage 1, stage efficiency becomes, suppose here for stage 1 we have to take the first stage 1, the stage efficiency becomes delta S is equal to WS1 divided by WA1. For one in the what S1 is indicating the stage 1, A1 is indicating the actual work done at 1. So from this again we have to write this WA1 is considered taken this side, so it becomes what? WS1 by neta S. WS1 by neta S. Okay. Okay. So next for stage 1 we have to write this neta S is equal to WS1 by WA1. So from this we can write this WS1 by neta S. Similarly for stage 2, same for stage 2, WA2 is equal to WS2 by neta S. For stage 3 we are having WA3 is equal to WS3 by neta S. So here total work, this total work absorbed, WA is equal to what? WA1 plus WA2 plus WA3. That total work here. Hence WA is equal to WS1 plus WS2 plus WS3 plus so on divided by stage efficiency. Okay, stage efficiency. So WA is equal to, so you can write that summation of I is equal to 0 to I is equal to K, that WS divided by, so all these work done are written in the summation of K 0 to K, that is here it is equation number 2. So equating the equation number 1 and 2, 1 and 2, where is the equation number 1? Here equating the equation number 1 and 2. Equation number 1 and 2. So here Ws by neta naught. So this is Ws by neta naught is equal to summation of phi is equal to 0 to k into W S I divided Si divided by neta s. This is not 1 Si. Okay. So that neta naught is equal to, from this we can get neta naught is equal, just we have to take this side, neta s Ws by summation of these. So at the constant pressure lines are diverging in the nature towards the right hand side of the temperature. Okay, temperature entropy diagram. The isentropic work per stage increases. The isentropic work per stage increases as the temperature differences increases. As the temperature difference increases for the same pressure issue and stage efficiency. For same pressure issue and stage efficiency. So from this we can get Ws is which is, so this term is less than 1, which is called as a for as preheat factor. This is a preheat factor. So neta naught is equal to neta s into preheat factor. The overall efficiency of that compressor can be obtained by stage efficiency into preheat factor. Okay, so this is the regarding the preheat factor, effect of preheat factor on the compressor, or prove that preheat factor is always less than the unity, always less than the unity. So the similar derivation is there for the turbines. So that we will discuss it in next class. Okay, and thank you. Go through this video, and if you have any doubts, ask. We will get in online and we'll go through that discussion.